We are wanting to build a box, and our box is needing to hold some items, and the length needs to be 1.5 times the width of the box. The volume of the box needs to be 2 cubic feet. So we just have a regular rectangular box, so volume is length times width times height. And so the length times width times height needs to be 2 cubic feet. With the materials that I'm using, the front and the back are going to be using the most expensive materials at $8 per square foot. The bottom is just going to be plywood, and so it's going to be the cheapest at $2 a square foot. The sides are going to be made out of slightly less expensive materials at $6 per square foot. So our overall cost is going to be the cost for the bottom, and the bottom is just a length times a width, and it's $2 per square foot. And then I'm going to add to that the cost for the front and the back. So the front and the back is going to be a length times a height, and I have two. I have a front and a back, and it's going to cost $8 per square foot for the front and the back. And then I'm going to add the cost for the sides, and the sides will be width times height, and there's 2 sides, and each of them is going to have a cost of $6 per square foot. So my overall cost then is $2 times length times width plus 2 times $8 times length times height plus 2 times $6 times width times height. Now I have 3 variables here, and it would be nice if I could trim it down to just one variable. I have enough information up here that I can do that. All of the lengths can be replaced with 1.5 times the width, and I can use the information about the volume to get an expression for the height. So first, why don't we replace all the lengths with 1.5 times the width. And then we know that the length, which is 1.5 times the width times the height, that needs to be 2 cubic feet. So that means that the height needs to be 2 divided by 1.5 width squared. Width times width is width squared. So I divide by 1.5 width squared and I get my height. So where height shows up in my formula, I can replace it with this expression here. So that will give me 3w squared, because 2 times 1.5 is 3, and w times w is w squared, plus 16 times 1.5 is 16 plus 8, which is 24. And that'll be w, but h can get replaced with 2 divided by 1.5 w squared. And then 2 times 6 was 12, so 12 times w, but then h can get replaced with 2 over 1.5 w squared. I probably want to clean this up a little bit more, so this term can't be reduced anymore, but here, this w cancels into one of those, and so I can rewrite that as 48 divided by 1.5 w to the first power, because this w canceled one of those. And then similarly here, this w cancels one of those, and I get 24 over 1.5 w. Notice these have the same denominator, so I actually can combine them. I can add them together, and 48 plus 24 will be 72 over 1.5 w. So that's the expression for my overall cost. My overall cost is 3w squared plus 72 over 1.5 w. going to be 3 times w squared plus 72 over 1.5w, but 72 divided by 1.5 is 48. And so I simplified 72 over 1.5 into the fraction 48 over w. Now from calculus, we know that we find minimums and maximums where the derivative is 0. We know we find minimums when our graph is concave up and our derivative is 0. So we're trying to minimize costs, so I want to find a point where the graph is concave up and the derivative is 0. So let's first find the derivative of the cost. And so the derivative of 3w squared will be 6w. And look at this term as 48 times w to the negative 1 power, because it'll be easier to look at that as a power rule versus a quotient rule. So 48 over w is 48 times w to the negative 1 power. So the derivative will be negative 48 w minus 2 will be the new power, because remember you always subtract 1 when you're doing the power rule and finding derivatives. So negative 1 minus 1 is negative 2. So that's the derivative of my cost. I want to know when that derivative will be 0. So I want to set the derivative equal to 0. So I'm going to add this to both sides. So we get 48 times w to the negative 2 is equal to 6w. Notice this term was negative, so I added it to the other side to make it positive. If I divide both sides by 6, I get 8w to the negative 2 is equal to w. And you might want to actually rewrite that negative power back in fraction form when we solve the equation. It might make a little more sense when you're solving the equation. I'm going to actually multiply both sides by w squared, because then we get the nice equation 8 equals w cubed. And if I take the cube root of both sides, that gives us that the width has to be 2 feet. So it looks like I'm going to get a minimum cost when we have a width of 2 feet. It might be helpful to double check that our graph is concave up at that point, because this could be giving us a maximum cost. So if I find the second derivative, so I take the derivative of the derivative of 6w will be 6. You know, it's just a linear term with slope of 6. Doing the power rule again, but with a power of negative 2 now, negative 48 times negative 2 is going to be positive 96 w to the negative 3. And I can just stop right there. 6 is positive, and whatever width I plug in for w, that's going to be 6 plus positive 96 over the width cubed. That will always be positive. So because my second derivative is positive, I know that my graph is concave up, and therefore where the derivative is 0 is where there's a minimum. So we need the width to be 2 feet. The length is supposed to be 1.5 times the width. So 1.5 times 2 is 3 feet. And the height needs to be 2 divided by 1.5 w squared. So if I plug in 2 for w, that gives me 2 over 4 times 1.5, or 1 over 2 times 1.5, or 1 over 3. So my height is only going to be 1/3 of a foot. So my box is going to be short, but it'll have the appropriate length and it'll have the appropriate volume. So I want a height of 1/3 of a foot, a length of 3 feet, a width of 2 feet. My cost, which will be my lowest cost, will be 3 times 2 squared plus 48 divided by 2. 3 times 2 squared is 12. And 48 divided by 2 is 24, giving me a minimum cost of $36.